Hello and welcome back to the course on machine learning. Today we're going to talk about a specific aspect of the k-means algorithm, which is the random initialization trap. So let's have a look at this phenomenon and see what it's all about. So, random initialization trap. So here we've got a scatter plot, again with two variables. So we've got the x and y coordinates. And in this case, let's say we're going to choose three clusters. So right away you kind of tell which is the final result. What is the final result going to look like if we choose three clusters? It does look like you can pretty easily spot them here. But let's nevertheless perform this operation, this algorithm. And if we initialize our centroids like this, then what we'll get is, because we already kind of can tell that probably that's a cluster, that's a cluster, and that's a cluster. So just to make the algorithm a bit faster, so we don't have to do too many easy steps and iterations, we're going to select our centroids like this. And right away, if we perform the algorithm, we'll get these clusters. And next is, even if we move around the centroids, so we find the centroids of each of these clusters, nothing's going to change. So you can, in your own time, you can perform the steps that we learned about in the previous tutorial and see that nothing will indeed change because of the way we selected the centroids. This is already the final result. So those are going to be the clusters that we're going to end up with. So that's kind of the end result of the k-means algorithm, because we selected the clusters, the centroids, in the places where we did. Now, the question is, what if we select the centroids in different locations? Will we be able to change the result? Will the result be different? And of course, an algorithm has to be, what we want from this algorithm is for it to give us a deterministic result, because we can select the centroids at random, and therefore we don't want that selection of centroids to affect how the clustering is going to happen. But let's have a look and see what happens. So what will happen if we had a bad random initialization? So bad is like a term we're going to use loosely for now, but you will see why we're using bad random initialization just now. So again, we're going to go through these steps that we discussed in the previous tutorial. We're going to choose the number of clusters, which is 3. We'll select at random 3 points, which will be our centroids. We'll assign each data point to the closest centroid that will form k clusters. We'll compute and place the new centroid for each cluster, thinking in terms of center of mass or center of gravity. And step 5 will reassign each data point to the new closest centroid. If any reassignment took place, we'll return to step 4. Others will go to the end because the model has converged. So these are the steps we discussed previously. Let's have a look at them in action. All right, so 3 clusters, and this time, instead of selecting the centroids here, here, and here, what we're going to do is we're going to select them differently. We're going to select the centroids like this. So we'll put one centroid here on this side, one centroid here, and one centroid here. So let's have a look what happens now. If we draw a line, so this time we have 3 clusters, 3 centroids, but the principle is kind of the same. We still have a point which is equidistant from all 3 of them. So this point over here is the same distance from all 3. And then this line is equidistant from these 2. This line is equidistant from these 2. This line is equidistant from these 2. Again, this is not part of the algorithm. As part of the algorithm, you would just take each individual point, you look at this point, and you would see which centroid is the closest. So this time is green, you'd color it green. This one you check again, you'd color it green. This one you check again, color it green, and so on. Then this one is the closest to red, you'd color it red, and so on. But just to make things easier for ourselves, we're going to use this little hack. We're going to use these lines to say anything in this part of the chart is going to be closest to red, just because these are equidistant lines. Anything in this part of the chart is going to be green. Anything in this part of the chart is going to be blue. It'll just save us time. So based on this method, we can tell right away that this is the red cluster for now. This is the blue, this is the green. So now we've assigned each data point to the closest centroid. That's great. Now we're going to move on to step 4, and we're going to move these clusters. So we're going to recalculate, compute, and place the new centroids for each cluster. So there we can see that that is probably the center of mass for the red points, that's the one for blue points, that's the one for green points. So we move our centroids to the new locations, and now we're going to perform step 5. We're going to reassign each data point to the new closest centroid. So again, we're going to use that quick hack with the lines. Let's see how the lines will look like this time. There's our new equidistant point, and these are the equidistant lines. So this time you can see that nothing will change. The red points are all already in the red corner, blue points are in the blue corner, and green points are in the green corner. So nothing is going to change. There will be no reassignment, so we don't go to step 4. We instead go to finalizing the algorithm because it has converged. So there we go. That is our model. It is ready. And as a result, we have these 3 clusters. Now, these 3 clusters are different to what we saw at the start. So let's have a look. This is what we saw at the start. We're going to call them the true 3 clusters because you can tell just from the chart, you can tell that these points would most likely form a cluster, these would form a cluster, and these would form a cluster. Just by looking at it, you can intuitively tell that is the case. This is what we got at the start of the tutorial, and this is what we got now. So you can see that the 3 clusters are different, and therefore what we have is a situation or a phenomenon where the selection of the centroids at the very start of the algorithm can potentially dictate the outcome of the algorithm. And that's not a good thing because the centroids are selected at random. So how do you combat this? How do you battle this? Well, the answer is actually not as straightforward. There is a addition or a modification to the k-means algorithm that allows you to correctly select the centroids. And the solution here is the k-means ++ algorithm. Now, at the same time, I wanted to mention that we're not actually going to delve deeply into the k-means ++ algorithm and how it's structured. You can definitely read up more about it on Wikipedia or other sources. It is quite a involved approach in how that selection occurs. But the good news is that all of this happens in the background. So the k-means ++ happens either in R or Python or whatever tool you're using. You don't need to actually implement it. So it's just a good idea to be aware of this issue, that there's a true cluster result that you're after, and there can be some false or some non-desirable clustering results, clustering outcomes of the k-mean clustering algorithm. It's good to be aware of that issue, and it's also good to know that the tools that you use will be, or make sure that the tools you're using are going to be implementing that specific selection of the random centroids at the very start so that you get the good result. So definitely, if you are more interested to learn more about the k-means ++ algorithm, definitely read up about it. But otherwise, it's not something that you really have to worry about. It's just something that you need to keep in mind and make sure or be confident that the tools you're using are bypassing this initialization trap. So hopefully you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy machine learning.